The following table shows the total number of effects, and the percentage of effects which are main effects or two-way interactions for a given number of factors. Based on the sparsity of effects principle, it is apparent that as k increases, the efficiencies of the full factorials decrease. Two problems with full factorial design with large k. Too many runs. Many times we are trying to run designs with large k and the number of runs needed for the full factorial not acceptable. For example, if we have 7 factors, we need 128 runs to complete the design. Usually this resource cost is too much. Based on what we saw on the previous slide, the majority of effects being estimated are higher order effects that will almost always be dropped anyway. Let's spend some time thinking about the term parsimony. Yaron referred to this as separating the vital few from the trivial many. The number of important factors is usually much smaller than the number of factors initially in the experiment, especially when k is large. This is also known as the Pareto principle. In the last couple of sections we talked about a 2-cube design. This is a design in which we have 3 factors, each of which have 2 levels. Here is the design with the +/ designation for the levels. Now right before you are about to run this design, your boss comes and tells you that we need to add another factor, but we can't increase the number of runs. How are we going to add this factor? What should the levels be? We know that we need to have the same number of pluses and minuses, so here are some possibilities. How do we decide which one to use? In order to decide this, we need to introduce 2-kp designs. A 2-kp design is a design where we get information on k factors with only 2-kp runs, instead of 2 to the power of k runs. Of course k is the number of factors. 2-kp is the number of runs in the experiment. P represents the extent of the fractionalization. The design uses 1/2 p of the runs from the full factorial. Now let's look at an example, 2-4-1. There are 4 factors. The level of fractionalization is 1/2. There are a total of 8 runs. Notice that this is 1/2 of the number of runs in the full factorial, which is 16. Pause the slide and try this exercise. The solutions will then appear. For our 2-4-1 example, how do we know which of the 16 runs to include in our 1/2? Fraction design? Well, we need to decide which terms to confound with factor d. The effect of 2 or more confounded terms is a linear combination of the true effects of each of those terms. So in other words, if d is confounded with abc, then the effect for this chain is a linear combination of the effects for d and abc, or denoted as d plus abc. The problem here is that for a large effect, we cannot tell if the majority is coming from d or abc. In this case we would assume that the large effect is due to d. This is because abc is a higher order term that we will usually deem not active. If we were to run the full factorial, 2 to the power of 4, we have enough df to estimate all 15 effects. And the mean free and clear, which means not confounded with anything else. 4. The 2-4-1 design, we only have 8 df. So we will estimate 8 effect chains made up of 2 confounded effects per chain. This is the balance for the fractional factorials. Even though we run less runs, we cannot estimate all effects free and clear. In order to determine which effects are confounded with each other, we use something called mod 2 multiplication. Assume that any combination of letters is considered a word, such as AB, ABC, etc. Since the columns in the design are made up of -1 and +1, we will multiply the terms together and reduce as follows. 1. If a letter has an odd number for a superscript, then it is left alone. 2. If a letter has an even number for a superscript, then it is dropped from the word. This occurs because axa equals a-2 equals I, since any term multiplied by itself is a column of ones. We will refer to this as column I. Also, any column multiplied by a column of ones will yield that initial column, so axa equals A. For our 2-4-1 design, We set the confounding for D to be ABC, so D equals ABC. This means that when we pre-multiply D by the equality D plus ABC, we get I equals ABCD. ABCD is considered the generator of the design. All of the other confounding patterns can be generated from ABCD. Now let's go back to our previous question. Using the generator, find the confounding for the design. This explains the remaining confounding for the design. 11. Here is the confounding or alias structure for the entire design. Are you comfortable with this design? What do you think is the weakest part of the design? Here are the results from a 2-4-1 experiment. Here are the effects for this experiment. Do these effects only represent the factors listed? What do you think is active based on the results? Is there anything else that you could do with these effects to get a better idea of which chains are active? Now we have set up our 2-4-1 design and are about to run this in random order, of course, when in walks your boss's boss and tells you that we need to add another factor. Now, since we have already used the three-way, we need to choose one of the two ways to confound with factory, so we let E equals AB. Now, let's take a look at how this affects the design. Write out the generators for this design, then complete the alias structure for the design. Does this explain the confounding? What do you think is the weakest part of this design? The defining relation of a design is a set of words that will be used to define all of the confounding in the design. It is made up of I and the generators of the design. We also need to consider the fact that since the generators are just a set of columns of ones, then any product of the generators are also a set of columns of ones. We call these generalized interactions and will include them in the defining relation. So for the 2-5-2 design, we have generators, ABCD and ABE. Now the product of the two is CDE, so the defining relation is I equals ABCD equals AB equals CDE. You should also notice that each effect will have 2p-1 aliases. The number of words in the defining relation should be 2p. Try this exercise. For 5 factors, let's set up a half fraction design. This, of course, is a 2-5-1 design. Here is the design matrix. Notice that it is a full factorial in 4 factors, then we let E equals ABCD to get the levels for E. Here is the full alias structure for the design. The weak point about this design is that two-way interactions are confounded with three-way interactions. I would not consider this a problem. Why do you think that is? Go ahead and repeat the process for the generator ABCE. I would pause the slide here and try this. The answer is on the next slide. You should find that the weak point of this design is that two-way interactions are confounded with each other. Why is this a problem? It seems that the first design is better. This is because we have all main effects and two-way interactions free and clear of each other. This tells us that for a half fraction design, it is best to confound the remaining term with the largest interaction. How do we decide on these generators to minimize the influence of the weak parts of the design? We will look at something called design resolution. The resolution of the design tells us the weakest parts of the design. A resolution 3. Design is one by which main effects are confounded with two-way interactions. It is usually used for screening designs and when resources are quite scarce. I would not recommend using a design with resolution less than 3. Resolution 4 designs are such that the weakest points or two-way interactions are confounded with each other. Resolution V designs are ones where the weakest point is two-way interactions confounded with three-way interactions. The higher the resolution, the better for estimating effects free and clear. Usually, People are most comfortable running resolution 4 or V designs. To emphasize the design resolution, it is usually denoted as a subscript. 2. Determine the resolution of a design. We find the word in the defining relation that has the smallest number of letters, except I of course, and that is the resolution. Pause the slide and try this exercise. To set up the general fractional factorial design. 1. Set up the full factorial and the number of runs that we have. 2. Set up the confounding for remaining factors. 3. Use this to get the levels for each run for those factors. 4. Then create the defining relation and find the alias structure. You want to make sure that the resolution is as large as possible. Pause the slide and try this exercise. The answer to the first question is in the white box. The answer to the next question is on the next slide. Realize that there is more than one right answer here. This is an example of an eighth fraction design. This means that we will take 1/8 of the runs as our design. So in the 7-factor 16 run case, the total number of runs had better be 16x8 equals 64 equals 2/7. Pause the slide and try to create this design. The answer is on the next slide. If we create another design using the given generators, you should be able to convince yourself that this design is resolution 3, which makes the design on the previous page better. This tells us that for any design with the level of fractionalization larger than 1, we should not confound the largest interaction if possible. Up to this point, we have been talking about a situation where the experimenter only has a small fixed number of runs to work with. What if someone has a much larger number of runs to work with? Should we still run the full factorial? 4. Example, if a person has 7 factors, should we run all 128 runs in the full factorial? My answer is no, but we still need to run enough runs so that we can estimate all of our important effects free and clear of each other. In this case, we would consider this a Res V design. How do we decide on what design to run? We first need to calculate how df we need to estimate all of these effects free and clear. This also includes 1 df for the mean. We know that we need 1 df for the mean, k for the main effects, and k1/2 for the two-way interactions. So this is the number of runs that we need at least. In order to decide on a design, we should find a design in which the number of runs is as close as possible to the number we need without going under. Here is an example for k equals 5. We need a total of 16 runs. Since we have 5 factors, we can plug what we know into the equality above and solve for p. In this case we need a half fraction or p equals 1. Here is an example for k equals 5. We need a total of 16 runs. Since we have 5 factors, we can plug what we know into the equality above and solve for p. In this case we need a 1/2 fraction or p equals 1. Here is the design with response. Notice that there are 8 runs in this design. Since we have 7 factors, this is a 2/7-4 design. Pause the slide and take some time to do this example. The results are on the remaining slides. Here is the alias structure. Notice this only goes up to order 3. What is the resolution for this design? Based on this, it seems that the alias chain that includes factors b and d are active. Here are the effects and their STD errors. We should still check for equal variance. Now recall that I spoke about Levene's test not being very powerful for a test with a small number of observations, and 8 should be considered small. We conclude here that both the chains with b and d are active, but we can't tell which effects in the chains are causing the large effect. We need a way to break these chains, and we will see it in the next lecture. Next time we will talk about 8 and 16 runs design more in depth and fold over. Designs.